Hello everyone, I'm Tianning She from Texas State University. Today I present the paper Precise Scheduling of Mixed Criticality Tasks on Varying Speed Multiprocessors. In conventional real-time system analysis, each system parameter is specified only one estimates. That must pessimistically cover the worst case. It requires high capacity of resource and platform. In other words, it leads to utilization waste in actual runtime. So, mixed criticality has been proposed to reduce such pessimism. In mixed criticality model, a set of tasks with different criticalities shares the same platform, and each high criticality tasks in task set with a multiple worst-case execution time estimates indicates different assumptions. Many works on MC model separates the tasks with two different criticalities: low criticality tasks and high criticality tasks. Low mode and high mode is to indicate less pessimistic assumption and the most pessimistic assumption respectively. The majority of works on MC scheduling is based on approach that low criticality tasks are sacrificed for giving the high criticality tasks extra space for extra workload, so that it guarantees all high criticality tasks meet their deadline. But in some applications, it is argued that low critical tasks is not equal to non-critical tasks. Dropping the low criticality tasks could be problematic. As a result, the concept of a precise mixed criticality model has been proposed, which is based on varying speed to separate two assumptions. There are two benefits in precise mixed criticality model. First, it gives a guarantee that all low criticality tasks not only execute on low mode, but also fully executed under the high mode. Second, the platform can execute under a lower speed in low mode when less pessimistic assumptions are fulfilled. That leads to the energy efficiency, which is very important for embedded system design. In this paper, we use a precise scheduling on multiprocessors. In our model, we assume that all processors will change their speed simultaneously. In low mode, the speed of all processors is energy conserving speed rho, which is larger than 0 and less than 1. In high mode, the speed of all processors comes to the normal speed 1. We also use implicit deadline sporadic task set in our model. Each task has two worst-case execution time estimates, CI low and CI high for low mode and high mode respectively. For low criticality tasks, its CI low is equal to CI high. By contrast, CI low is less than CI high for all high criticality tasks. Our model assumes that the system starts at low mode. When high criticality tasks exhausted its CI low budget in low mode but still not finished, the mode switch is triggered. The system turns into the high mode. Additionally, The difference between the two budgets of high criticality tasks, CI high and CI low, is compensated by improved speed when mode switch is triggered. When a job in a high criticality task exhausted its CI high budget but still not completed, that is considered as erroneous and would be terminated. Our problem is guarantee all deadlines are met for both low and high mode. Additionally, all processors must operate at an energy conserving speed rule if all jobs finish with a CI low budget. And all processors may operate at normal speed 1 if mode switch is triggered. Based on this model, we proposed a new virtual deadline-based scheduler FP-EDF-VD as well as a new fluid scheduling algorithm MCFFR. The first algorithm, FP-EDF-VD, is composed of FP-EDF and EDF-VD. FP-EDF is for scheduling an ordinary sporadic tasks on multiprocessors. It separates a task to two types of tasks, high utilization tasks and normal tasks. FP-EDF uses a fixed priority scheduling to schedule the high utilization tasks. They are statically prioritized over other tasks. For other tasks, FP-EDF uses a global EDF to schedule. It also gives a sufficient schedulability test. Our schedulability test is based on this. In EDF-VD, it assigns all tasks with a virtual deadline on the low mode. For low criticality tasks, their virtual deadlines are set identical to their actual deadline. By contrast, for high criticality tasks, their virtual deadline is smaller than actual deadline. The distance between the virtual deadline and the actual deadline of high criticality tasks is used as a space for potential extra workload of jobs of high criticality tasks which are released in low mode and have the virtual deadline after mode switch. In other words, it only gives each high criticality tasks a virtual deadline in low mode. EDF-VD set a system-wide parameter x to decide the virtual deadline. In runtime, under the low mode, all tasks are scheduled according to EDF by their virtual deadline. On the high mode, EDF scheduled high criticality tasks by their actual deadline, and the low criticality tasks are dropped. Our FP-EDF-VD has a two-phase. First one is choosing X with a given energy conserving speed rule. The difference between the EDF-VD and our model is that we give all tasks a virtual deadline which is smaller than their actual deadline when the system is on the low mode, and keep low criticality tasks on the high mode. We proposed our sufficient schedulability test. If this test is passed, we set the virtual deadline to all tasks. The second step is runtime phase. It is mapping our task set to the non-MC sporadic task set. The task set is separately mapped depending on different mode. Under each mode, our algorithm will apply FPEDF respectively. In other words, we have two mappings from MC tasks to non-MC sporadic tasks. And upon a model switch, FPEDF is relaunched with respect to a different set of non-sporadic tasks. We also give the speedup bound of FPEDF-VD. Speedup bound is how much faster processors are required for an algorithm to schedule the same task set scheduled by an optimal algorithm. Our algorithm FPEDF-VD has a speedup bound is less than 4. We proposed virtual deadline-based approach FPEDF-VD and give it a speedup bound. We also have another approach, MCFFR, based on idealistic fluid scheduling. In fluid scheduling, each task may receive a fraction of a processor and have a constant execution rate, even if the number of the tasks exceed the number of the available processors. When it comes to MC scheduling, there are two constant execution rates for high criticality tasks due to two different worst-case execution estimates. We can describe it on this figure. The red line indicates the high criticality tasks. The system starts at the low mode. In low mode, high criticality task requires a constant execution rate, which is larger than its utilization. It is to create enough space for additional execution requirements when the mode switch is triggered. In high mode, high criticality tasks require even larger speed after mode switch. By contrast, low criticality tasks have only one constant execution speed on the both low mode and high mode. We use a blue line to indicate it. To make the fluid scheduling feasible, it is requires that the summation of the rates of all tasks does not exceed the platform capacity, and also requires that the rate of each individual task does not exceed the speed of an individual processor. So we give our settings of execution rates for satisfying those requirements. For each low criticality task, we assign a constant execution rate for both modes, and it is equals to its utilization. By contrast, we separately set a constant execution speed on the low and high mode for all high criticality tasks. The lambda is a ratio of constant execution rate of high criticality tasks in low mode and the rate in high mode. It is a constant, a fixed ratio. That's why our algorithm called MCFFR. The assignment of lambda and the theta I for all high criticality tasks are as shown. Based on requirements and settings, we give our sufficient schedulability test. Also, we proposed the approximation ratio of MCFFR. The approximation ratio is the ratio of energy conserving speed determined by an algorithm compared to optimal algorithm. The smaller the ratio, the closer is the approximation to the optimality. After proposing the virtual deadline-based algorithm FPEDF-VD and the fluid scheduling MCFFR, we evaluate them through the schedulability ratio on the 1000 randomly generated task sets. In this figure, the horizontal axis indicates the U-bound, which is the total utilization of each identical processor in high mode. The vertical axis is the ratio of the number of the task sets which are successfully scheduled by algorithm versus the total 1000 random generated task sets. At this point means that on the 8 processors with a half normal speed as an energy conserving speed, when the per core utilization in high mode is equal to 0.2, FPEDF can schedule about 20% of the randomly generated task sets. Under the same number of 8 processors and energy conserving speed, when the relative system utilization is equal to 0.2, MCFFR successfully scheduled about 80% of total task set. In summary, we presented a new MC model with a varying speed, system-wide energy conserving speed rho in low mode, and a normal speed 1 in high mode. Meanwhile, low criticality tasks are fully executed not only in low mode, but also in high mode. And we give the problem statement under our mode. Based on that, we proposed a virtual deadline-based algorithm FPEDF-VD and the fluid scheduling MCFFR with a sufficient schedulability test. We also proposed and approved a speed-up bound for FPEDF-VD and approximation ratio for MCFFR. Finally, we evaluate these two approaches with our empirical schedulability experiments. Thank you.